short break. Thanks. Thanks, everybody.
Okay, it's a great pleasure for me to start the last session of the day. This is a keynote talk with the title of Locality in Computation by Ronitt Rubinfeld from MIT. Ronitt is a professor in the Department of Electrical Engineering and Computer Science and a member of the Computer Science and Artificial Intelligence Laboratory. Ronitt's main research area is the theory of computation. Ronitt received her PhD from the University of California at Berkeley in 1991. And prior to that, graduated from University of Michigan with a BSc in Electrical and Computer Engineering. Before coming to MIT, Ronitt had postdoctoral researcher positions at Princeton University and Hebrew University. In 1992, she joined the Faculty of Computer Science Department at Cornell University, where she was an ONR Young Investigator, a Solon Research Fellow, and the 1995 Cornell Association for Computer Science Undergraduate Faculty of the Year, as well as a recipient of the Cornell College Engineering Teaching Award. From 1999 to 1903 to 2003, Ronitt was a senior research scientist in NEC Research Laboratories, and in 2004, she was a fellow at the Redcliffe Institute of Advanced Study. So without further ado, the floor is all yours.
Thank you. Okay, so I'm going to talk about local computation algorithms. I'm interested in what happens when the inputs are so large that you don't have time to view all the input. You just don't have time to look at it. And not only what happens when the inputs are so large that you don't have to see them, but you're trying to compute a problem that actually has a large output, and you don't have time to write out the whole output. Okay, so this is the problem, but perhaps the user is in a situation where they don't actually, because the output is so big, they don't actually want the whole output. They want query access to the output. Okay, and when you don't actually need the whole output, you just need the ability to reach any part of the output that you want. Maybe you don't need to compute the whole output. Maybe you can just answer the queries of the user and not actually compute the whole output in order to answer about those pieces that the user wants to see. And maybe if you don't need to compute the whole output, maybe you don't even need to see all the input, which would be great because it's huge and it's too big to view. Okay, so what we're interested in is questions of locality and computation. Now they come up. Locality and computation has come up for decades in distributed computing. It's an issue in massively parallel computation. People that are interested in PageRank algorithms on huge graphs or any sorts of partitioning are interested in how can I compute these things locally. Today, I'm going to talk about a model called local computation algorithms, which tries to give a model that formalizes these types of questions in the sequential model. So what I'm going to talk about today is all sequential, although it will make use of notions in distributed computing, and it's also useful in parallel computation because many of the techniques can be shared. And another place that is interested in such types of algorithms is sublinear time approximation algorithms. Finally, one place that many of you may have seen such questions before is local decodability, where they're exactly interested in these types of questions. Okay, so in the outline of the talk, I'm going to talk about our formalization of a local computations algorithm model. I'm going to give some examples. So a traditional example that I always give is maximal independent set. I'm also going to talk about a more recent and kind of simple result on interval job scheduling, just to show that other types of problems can be solved with different types of techniques. And finally, I'm going to talk about newer questions in uniform generation, local ways of generating very large random objects. And if I have time, then I may go on to more uniform generation results in a somewhat different model than the local computation algorithms model that I'll define in the next few slides. Okay, so that's the plan of the talk. And let me start with maximal independent set, which I think is a question that needs no introduction in this crowd. I just want to say I want to compute maximal independent set. Let's assume the graphs have bounded degree, let's say degree at most delta. And the type of question we're going to ask here is you're given some query to an output. You're asked, is node U in the maximal independent set? And you're supposed to answer yes or no. Yes, U is in the maximal independent set, or no, U is not in the maximal independent set. And notice, I think one question that might easily come to mind to most people is, okay, you can always say U is in the maximal independent set. The point is we want to provide answers to users that query more than one node, and we want to do it in a consistent manner so that it's the same maximal independent set. So that's going to be the difficulty. Okay, so the first idea that might come to mind is the lazy greedy algorithm. Here, initially, the maximal independent set is empty. And the query would ask, okay, is node U in the maximal independent set? And you would see, this is one query you get. You've had some previous queries. You're going to have some future queries. So you'll check and see in your previous queries, did you ever put U in the maximal independent set, or did you decide it's not in the maximal independent set? Because if it's already decided from how you answered previous queries, you should answer consistently. The other thing you should do is look at the neighbors of U. Have you put them in the maximal independent set in previous queries? Because if you did put any neighbor of U in the maximal independent set in answer to a previous query, then you should not put U in the maximal independent set. But if none of the neighbors have previously been put in the maximal independent set, put U into it and remember this decision. Okay, so what's the requirements of this thing? Well, you need order delta time per query. Delta is the degree. So you need to look at all the neighbors. So you need to look at all the neighbors and see whether you put them in or out, or you haven't touched them yet. So you need order and space to keep track for each node, whether you, and if you have touched it, did you put it in the MIS or not? Okay, so this is sort of a very straightforward algorithm, but notice that the answer depends on the query order. And you have to remember your past choices. And so one thing you cannot allow is simultaneous non-interacting copies of the algorithm. Like I can't say, okay, there's some graph up there in the cloud, and I have different agents that answer maximal independent set answers in a consistent manner. All right. So now the question is, can we avoid these problems? I want to argue that these are important problems. And the example that I always give is when you're trying to seat students in a large class, like, our data structures class has 350 students, and you're trying to get them into an auditorium for an exam, and you don't want anybody to sit next to each other. So you have some graph on the seats of where you're allowing them to sit. They're not allowed next to each other. They're not allowed, maybe you don't want them right behind, or maybe you want whatever constraints you have. So you have some graph on the seats that's telling you who are neighbors, meaning you don't want them to, you put an edge between two nodes if those represent seats where you don't want people to sit in both of those seats. And now the students come in at the last minute, and quickly you and your course staff have to seat these people and make sure that you're getting a large independent set. And you have to do this without talking to each other because it's all going so fast that you don't have time for communication. Okay, so this is I'm claiming this maximal independent set is a crucial problem for all of us. Okay, so what's the difficulty? The difficulty is there could be multiple legal outputs, and how do you stay consistent? Okay, so here's a model. This is a model that was proposed by myself, Tamir, Vardy, and Shi, and we call it the local computation algorithms model. It is a model about serial computation. So it is sequential computation. So it's sequential computation because the name is too similar to the distributed local model. Some people prefer to call it the centralized local model. So either of these names gets used in practice. Okay, and in this model, you have a very large input X, and that is written down. You have random access to it. And there's a very large output Y, which is not written down. And that's what you want to figure out. Okay, so now some user wants to access this large output Y. So we build this query processing algorithm called the local computation algorithm, which can make probes to the input. And it'll get some query. The user will say, I want to know what's the value of Y at location I1. The LCA will make probes to the input at various places and say, oh, okay, the value of Y at location I1 is Y sub I1. Then the user comes and asks, okay, what about location I2? Then the LCA makes more probes, or maybe it already knows the answer, and then it answers Y sub I2. So there's some sort of give and take here. And this is the basic model. Okay, but what we'd like to support is actually swarms of LCAs, meaning lots of LCAs, but notice that these don't talk to each other. They can initially share a short random string, hopefully polylogarithmic size, but after that, they compute independently. So this is not a distributed network, but these are copies of the algorithm that should agree on the output. Okay, so what we'd like is the user there's a bunch of users now, they can ask any one of these LCAs for their answer. And these LCAs need to provide the illusion of a fully constructed output. Okay, so if they get asked about different areas of the maximal independent set, they should output in some way that could be put together into a single maximal independent set. Certainly if they get asked the same queries, they should be consistent in their answers. So there should be some consistent solution that is consistent with all of the answers. Okay, so that's the model here. Okay, and what we'd like from these LCAs is that they use sublinear time, space, and randomness. And in particular, it would be great if they didn't have to remember their past decisions. Okay, so this last part is the part of the model I'm going to change if I get to the second part of my talk. Okay, or the last part of my talk, let's call it that. So for now, though, we'd like sublinear time and space, and that they don't remember anything they did in the past. So you can even think of it as each of these copies of the LCAs, they answer one question and then they sort of die. And then another copy of an LCA who has the same short random string, but no memory at all, completely wiped out, gets asked the next question and then it dies. And then there's another LCA that's kind of born, again, no memory, same random string, and it gets asked a completely different question, but somehow when you put the answers together, you get something consistent. That's the goal. Okay, so it maybe sounds crazy. How can you even do this? But it turns out you can. So how can we design good LCAs? And one of the main techniques is to look at the fact that distributed algorithms has done so much in locality of computation that you can just use a lot of these insights directly in constructing LCAs. Okay, so why is there a connection between local distributed algorithms and these local sequential algorithms? And this is an insight of Parnas and Ron that's super important. Okay, so what it says is if there is a k-round distributed algorithm for any problem, say maximal independent set, then it has to be that V, if you ask about a node V, okay, what is its solution after k rounds? It can only depend on the k radius ball around V. Okay, so whatever the answer is after k rounds can only depend on the k radius ball. And so a sequential algorithm can go now and simulate what the distributed algorithm would do in all the nodes in this k radius ball. Okay, so you just sequentially read and simulate in delta, the degree, to the k, the number of rounds. That is the size of this ball. You can just probe the input in all these places and then simulate the distributed algorithm. Okay, so that is the insight. And now how good it is depends on what is delta, what is k. So delta for now we're thinking of as being a constant, but maybe k is really big. So what do we do about that? Okay, so let's see about MIS. Well, MIS already sounds not so good because lexicographically first MIS is P complete, but we can do this in randomized order log n rounds, but then maybe that's not so great because log n rounds, when you put log n in the exponent, you're not getting sublinear time. Okay, so just if there's one thing I want you to remember from this slide is that a log n round distributed algorithm doesn't really do much for us. Okay, so we're going to use insights from distributed algorithms, that's for sure. But log n rounds is already too much for us to just use with Parnas Ron. However, even when you have a log n round algorithm, some of the building blocks that got you the log n round algorithm can be used to give us a lot of help in designing LCAs. So the idea prime is to use the distributed algorithms to what is now called shatter the graph. Okay, so for example, if you do a certain number of rounds, like order delta rounds of a distributed algorithm, say you do Luby's maximal independent set, but just do order delta rounds of it. Don't do enough to actually solve the whole graph, but just do enough to do 99% of the graph. Question? Is there a question? Oh, there's a chat. Let me see what's in the chat. Oh, there's lags in the audio. Okay, I don't know.
I think it's best.
Is it really bad?
Just to continue. This is the best that we can do at the moment.
Sorry about that. Okay. Okay, so back to the distributed Luby. Hopefully the slides will give you an idea of what's going on. Maybe that's what we'll do. So as far as distributed Luby, you can run it and just do say 99% of the graph, get that worked out. And don't do it the full log n rounds. Just to get, you only need order delta many rounds to get a large constant fraction of the graph. Now, you're left with 1% of the graph that's not solved, okay? So the 1% of the graph that's not solved is not in one big clump that you don't know what to do with. It's actually nicely what they call shattered into small pieces. And each of these pieces is really tiny polylogarithmic size. So the idea is like, let's run Luby. Let's run Luby in the distributed algorithm, but then simulate it sequentially. So it's going to be order delta to the delta time. And then what we'll do is once we figured out if our node U is already solved, let's say it's not solved, okay? I see that U is not solved after delta to the delta. I do this delta to the delta processing. I see U is not solved. So I'm going to figure out the connected component of U that remains. And what we're going to show, is that the remaining live components are all small. And this is similar to an analysis due to Beck. And then we can just solve these live components we have to figure out who the live components are. And then we can solve them in polylogarithmic time. So by small, I mean polylogarithmic size. And then we can just solve them sequentially in polylogarithmic time. Okay, so this gives a delta to the delta time polylogarithmic time algorithm. Okay, it's not the best and it's been improved quite a bit. Okay, so the shattering idea was later used and improved by Barenboim et al. And Ghaffari and many others. So one can do a lot better. Okay, so that is one technique based on using distributed local algorithms. I want to mention another technique based on the greedy algorithm. And this is an idea that isn't based on a distributed idea, but actually there are later works of Shun and others that do similar things based on greedy for in the distributed setting as well. So it's not unconnected to distributed computing. It's just that the inspiration came from the greedy sequential algorithm. Okay, so it was based on an insight of Nguyen and Onak that said the following. Okay, so run through your node. What does greedy do? What we talked about greedy earlier. What does it do? It runs through the nodes in some order. Okay, and I'm talking now about the sequential algorithm. We'll see how to make it local in a minute. But what it says is, okay, run through the nodes in some order, put V in the maximal independent set if none of the neighbors are in the maximal independent set yet. Okay, and the LCA should compute what would greedy do on node U. Okay, so then you have to simulate the results of greedy for all the adjacent edges and nodes of you that have a lower ordering. Okay, so I have to work out, oh, that neighbor came before me in the greedy ordering, so he was figured out before me. But that neighbor, he comes after me in the greedy ordering, so I don't have to figure out what greedy did on them because greedy processed me before that other neighbor. Okay, so I have to look at all the lower ordered neighbors, figure out what greedy would do for them, and then I can figure out what greedy does for me. I don't need to know what greedy does on all nodes in the graph, just my neighbors that are lower ordered in order to figure out what happens to me. Okay, well, the problem is the dependency chains could be long. For example, maybe I am node 117. So I just have to look at my lower ordered neighbor. I have to figure, okay, let's start with 112. I'm at node 112. I have to figure out if 111 was put in to the MIS, but I know that the greedy algorithm didn't even touch 113 yet because I'm 112, okay? And the greedy algorithm is going in order. So I know 113 hasn't been put into the maximal independent set yet because he's still processing me. But he has looked at 111. So I have to figure out, what did he do for 111? And then 111 has to say, oh, what did he do for 110? And so on. So the dependency chain can be extremely long. Essentially, I have to figure out, in this case, I have to figure out if I'm an odd or an even number of steps from the start. So I really have to go down the whole length of the chain. So in general, dependency chains can be long, but the insight is that if we started with a random ranking instead of an arbitrary ranking, then with high probability, the random ranking dependency chains are short. And in fact, it's not just in expected value as was shown in earlier works, but you can show that for all nodes, the random ranking dependency chains are short. Okay, so it's using a little bit more work, you can show that. All right, so these are two ideas that give you LCAs for maximal independent set. Their dependence on n is polylogarithmic, but using a different distributed algorithm, Evan, Medina, and Ron, we're able to get a log star n dependence on n. As far as dependence on the degree delta, all of these early methods have exponential dependence on the degree delta, but we have been whittling away at that, and some recent results of Ghaffari and Wito have shown that very close to polynomial in the degree. It's delta to the log delta dependence on the degree. This is newish, it's actually 2 years old, but it feels new. And a big open question is, can you get polynomial in delta dependence for local computation algorithms for maximal independent set? Okay, so other problems considered in this model are, well, lots of problems have been considered, and also lots of problems have not been considered. So there's lots of open problems because almost all the problems not on this slide have not been considered, although I will give a few other examples in a minute. So lots and lots of open problems, but some things that are known is people have looked at maximum matching, weighted vertex cover. Some of these problems can be done polynomial in D. And in fact, there have been applications in the learning setting by Fagan, Mansoura, and Shapiri. Scheduling problems, I'm going to talk about job scheduling in a minute, a very simple one. Coloring problems, set cover, logical problems such as KCNF, any problem that's solvable by Lovász local lemma techniques of a certain type by Brandt et al., mechanism design, and online algorithms throwing balls into bins. Like if I throw balls into bins and use something like power of two choices, can I figure out which bin my ball got thrown into? Because do I have to go through and figure out all previous balls, which bins they were thrown into? Or can I figure out just a small number of balls and locally figure out, according to power of two choices, where my ball should have gone? Okay, so this is a non-exhaustive list. Sorry, I'm having trouble with I advance this. There we go. These are all polylogarithmic probes. And I just want to say again, this is all sequential. Okay. And let me just say a little bit more about interval scheduling. This is work with Spencer Compton, who's actually an undergraduate at MIT, and Slobodan Mitrovic, who was a postdoc and now is at UC Davis. This is, in here we have the input is jobs described by starting and ending time. So they're intervals. This is interval scheduling in which they must be scheduled. And our goal is to schedule as many jobs as possible with no overlaps. Okay, so I don't know if you can see, but these purple ones are the ones we're scheduling, and supposedly they have no overlaps. So that's the most we could get in. All right, so the LCA question would say, given a particular interval, xi, yi, is that one actually scheduled in this interval scheduling? And of course, there are many schedules that might be optimal, but I want to fix on one. All right, so I'm going to assume that we have access to a particular data structure, because otherwise, I mean, there has to be some ordering on these intervals. Otherwise, it's not going to be possible because we'll be looking for needles in a haystack every time we look for the next interval. So we're going to assume that there is some data structure that allows us to access these intervals in the following manner. We're going to call this data structure next finish. I'm going to be able to query a time t, and the data structure next finish will give us the earliest finishing job from all jobs that start after time t. Okay, so that's what that one does, and I've put it up here so that you can remember what it does. Now, if we're not worried about LCAs, we're just worried about solving this problem. Here's the optimal greedy sequential solution. We're going to start, we're basically going to schedule left to right. Okay, so we're going to start at time 0. We're going to find the earliest finishing job. So we're going to call next finish with time 0 and find the earliest finishing job in the whole data set. And when we get that, we're going to schedule that job. So that's our first XY. We're scheduling it. Now we're going to update our left side to be the last time of the last job scheduled. So now our new time is Y, because that's the ending time of the last job scheduled. Okay, now we're going to call next finish again. What starts after time t, but finishes earliest. Okay, we're going to schedule that, and we're just going to keep going this way left to right. This is the greedy solution, and it's known to be optimal. Okay, and we just do this till the end of time. So that's what greedy would do. It's optimal, it's known, and it's kind of something that we teach in undergraduate algorithms. So what's the insight that we're going to use to be able to do this in a local manner? What we're going to do is add breakpoints, okay? And they're going to be separated by theta 1 over epsilon jobs in the optimal. So these are not arbitrarily placed breakpoints. These are, I'm not just going to take the interval and then just break it in evenly spaced places. We're going to find a way of breaking it so that there's roughly 1 over epsilon jobs in each partition. Okay, so some constant times 1 over epsilon jobs in each partition. And we are going to figure out how to do that. But assuming I could do that, why is that good? Okay, well, notice that if on these red breakpoints, I can schedule at most one job that crosses this breakpoint, because these jobs have to be non-overlapping. So if two jobs if 2 jobs cross this breakpoint, then I have to pick one of them. Okay, so in most, one job can cross any breakpoint. At most, one job in the solution can cross a breakpoint. Of course, the input, I could have as many as I want over a breakpoint, but in the solution, I can have at most one job crossing a breakpoint. So if I throw out jobs that cross the breakpoints, and I don't have that many breakpoints, I'm not really throwing out that many jobs, right? Okay, so so what we're going to show is like there's not that many breakpoints, and they kind of account for it like some constant times epsilon n many jobs. So if I throw out all those jobs, I still get a good approximation to the best solution for interval scheduling, even if I throw out those jobs. Not that many. All right, so now what we gain from that is any collection of optimal solutions between breakpoints is going to be good for us. It's going to give us a 1 plus epsilon approximation. So we've now said, okay, throw out all jobs that cross these breakpoints, and now we've localized the problem. If I can solve the problem in each of these areas optimally, I'm all done. Okay, now if I want to figure out if this job gets scheduled in the optimal solution, I just have to figure out if he's in the optimal solution between these 2 breakpoints. Okay, so that's all we have to do. And that becomes a sequential problem in a much smaller area. All right, so why can we compute this sequentially quickly? We're just going to use the optimal greedy inside this area with access to this data structure. Okay, so I can do that quickly because the number of times I'm going to call this data structure is just theta 1 over epsilon, because that's how many jobs I need till I get between this breakpoint to this breakpoint. Okay, so this will happen quickly. Theta 1 over epsilon calls to next finish, and I'm done. Okay, the big problem that we're left with is how do we find these breakpoints? Okay, and the thing to notice is we have a lot of leeway. Really, any reasonable set is good. Okay, so here's one way you could do it. You could do it with a hierarchical choice of breakpoints. You take an interval, L to R. Now somebody asks you about job X comma Y, and you're trying to figure out, whether XY is scheduled or not. And you don't know where the breakpoints are yet because you're a local computation algorithm and your memory's been, you just don't know this yet. But you can add a breakpoint in the middle of L comma R. And then if XY crosses this breakpoint, just output no, it's not in the job. I mean, it's not scheduled. But if L is less than so if X is completely on one side, so if it crosses the breakpoint, forget it. But if it's completely on one side, let's say it's completely on the left side, then we have to figure out one of two things. Maybe the number of jobs in the that can be scheduled in the left side is small enough that I can just figure out the optimal solution. And if that's the case, I'm just going to figure out the optimal solution and see is X comma Y in the optimal solution. Okay, how do I figure out if the number of jobs is small? I just try to compute the optimal solution. I'm just going to use this next finish thing. I'm going to call it something like, I'm going to call it theta of 1 over epsilon times. And I'm going to see if I went all the way from the left side of this interval to the right side of this interval. If that's the case, then I know that the size of the optimal solution there is at most C over epsilon. Okay, and if I've computed the full optimal solution and XY is in the optimal solution, I'll output yes. Okay, if I call next finish C over epsilon times and I didn't reach the right end of the interval, then I have not computed the full optimal solution. So I'm going to recurse. I'm going to divide it in half again. Okay, and when I divide it in half again, I'm just going to recurse using this same thing. All right, so that's the whole idea. And that takes order 1 over epsilon times log n probes to answer for X comma Y, whether it's in the optimal solution or not. Okay, so this is just a third method of constructing LCAs, is to somehow find locality in the problem. Okay, I do want to mention, and I'm not going to say much more about it, another area where a lot of effort has gone into constructing LCAs is in finding sparse subgraphs with certain connectivity properties. So if you're given a graph G and you want to find a sparse connected subgraph of G, or if you want to find a low stretch spanner of G, and you want to provide query access, is edge UV that's in G, is it also in this low stretch spanner, or is it also in the sparse connected subgraph? Okay, so there's been quite a bit of work here and lots of ideas, but I'm not going to talk about that too much more right now. Okay, so, but one thing to say is one thing to say is the running times of these are not polylogarithmic. They're more like n to the 1/2, n to the 2/3, n to the 3/4, things like that. So they are sublinear, but they're not polylogarithmic. Okay, so one thing that's desperately needed is more techniques for handling large degrees and sparsifying the data. And so there has been some really nice work. For example, in SOTA 2019 has some really nice ideas for sparsification that's been useful in other contexts as well. And there's been work in the work of Parter et al. And later works that on how to get algorithms that are sublinear in the degree. But this is a place where I think a lot of focus is needed. Okay, I'm going to turn to a different topic, a slightly different topic. Instead of trying to solve problems and finding an optimal solution, I want to turn to the problem of generating random objects. And the type of random object I want to start with is generating random colorings of large graphs. Okay, so this is a, we're given some large graph. There's lots of colorings. Again, I'm going to assume maximum degree delta. And I'm going to say that you get a number of colors that's at least delta. But in fact, I'd like to take a lot of colors. So I'd like at least 12 delta colors. And the goal is output a uniformly random valid coloring of G. But we're going to give query access to the coloring. So there's a single coloring that's uniform, but the queries are going to be, what's the color of node V? What's the color of node W? And we'd like these things to be consistent with the same uniformly random coloring. Okay, and perhaps the user could end up by the end of time asking about every single node in the graph. So everything needs to remain consistent with the legal coloring, and whatever output you give should be uniform. Okay, but you'd like each query to be answered in sublinear probes to the graph. Okay, so before we go into local computation algorithms, let's just see what's known about coloring. And there is this basic, and this is a sequential Markov chain due to Jerome for the case where the number of colors is at least 2 times the degree, the max degree of the graph. And just to remind you what this does, it's a really beautiful Markov chain. It says pick random node V in the graph and recolor it randomly, and then check the neighbors of V and see if there's a conflict with its neighbors. It only has delta neighbors, and we just picked Q from a set of 2 delta colors. So with probably at least a half, there shouldn't be a conflict with neighbor. Actually, let me not say anything about that, but let's just say you have a good chance of not having a conflict with your neighbors. Okay, and if you don't have a conflict with your neighbors, then update V. Okay, so now do this n log n times. Just do this n log n times. You're going to hit each node because it's coupon collector. You're going to hit every node V, and eventually everybody gets its chance to be recolored, maybe log n times even. But eventually, after n log n steps, you can assume that this is a completely random legal coloring. Okay, and that was, that's a really nice result. We're not going to prove it in this talk or see why that's true in this talk. We're just going to use it. Well, we're going to use something that builds on that even. Okay, now what we're going to provide is a slightly stronger query, not just what is the color of node V at the end of this process, but what is the color of node V at time t. Okay, so of course, we're interested in the color of V at the very end of this process, but we need to be able to help the user by figuring out what's the color of node V at time t. Okay, to figure out what that would be, we'd have to figure out when was V last picked, which color did it choose? This is probably easy to do, but then we have to figure out, did it conflict with its neighbors? Okay, so then we have to look at all its neighbors. What was their color at the time? I have to figure out what was their previous random choice and what were the colors of their neighbors at that time. And so this can go on forever. If we just think like Parnas Ron, this could be delta to the t, because I have to go back in time, and each time maybe I go 1 step, or maybe I'd notice that actually when I look at W's previous random choice, node W only gets picked roughly log n times because we have n nodes, n log n steps. It means each node gets picked about log n times. So maybe I don't actually have to go back. Maybe I can make big jumps in time. Maybe there's some way I can cut it down to delta to the log n. I actually don't even know the answer if we can, but I'm not going to worry about it because there are going to be better ways to do it. Okay, because all these simple ideas still seem to be super linear in n. Okay. But again, distributed algorithms came to the rescue. So here's some modified Glauber dynamics. The distributive Markov chain rounds by Feng et al. And Fisher et al. say the following, and this is a distributive coloring, uniform generation scheme for coloring. Okay, so you have n nodes that simultaneously choose random colors. We're going to call these proposals, and we're going to update the color if there is no conflict with any neighbor's current color. That kind of makes sense. Or their new proposal. Okay, that makes sense too. And this next thing might seem a little extraneous, but it's important for making the Markov chain work. No neighbor's proposal should conflict with our current color, not just our proposal, but our current color. Okay, so that may seem weird, but it's important to make this work. So this thing works. Okay, and this thing needs order log n rounds. All right. Now remember in the beginning of the talk, I said log n rounds isn't so great for us because if you just use standard Parnas Ron technique, you get the degree delta to the number of rounds, which is order log n, and that's not necessarily sublinear. So as this stands, it's not good enough to get us a sublinear time sequential LCA. But I'm going to describe a method that does a bit better. Okay, and this is going to be an n to the alpha for alpha less than 1 time algorithm. And alpha, how big alpha is depends on how many colors you let me have. Okay, so the more colors you let me have, alpha will go down. I just need alpha to be, alpha depends on the ratio of the number of colors divided by the max degree. So I need some constant times the max degree many colors, and alpha is going to be a constant that gets smaller as the ratio of the number of colors to the max degree gets bigger. Okay. All right. So we're going to implement something called accepted, which asks, does V accept the proposal of color C at round T? And to answer that, in the first attempt, you might say, well, I want to know if, oh, okay. Actually, yeah, we just talked about this. This is the Feng et al. And Fisher et al. Thing. The first attempt is to figure out if V accepts the proposal of color C at round T. We'll look at each neighbor and decrement the time until we find the last accepted proposal in order to figure out for each neighbor what color they are. Okay, and that would be terrible. That would not give us a sublinear running time. But the insight is, I don't actually need to know that what my neighbor's color is. I just need to know that it's not C. Okay, I mean, I need to know what it's not. I don't need to know what it is. Okay, so what that allows us to do is for each neighbor, we can jump back to the previous time the color C was proposed and then increment forward to see if it's overwritten. And it turns out that most of the time it is overwritten. So the amount of work we need to do, I mean, most of the paths that we have to check to see if our neighbor has color C, most of them will die out quickly. And very few of the paths will we actually have to go and check for a long time. So it turns out we can save an awful lot of work in this manner. And that's why we get the n to the alpha time for alpha less than 1. Okay, so still, it's an open problem. Can you get polylogarithmic time for a Q? I mean, first of all, can you get polylogarithmic time, period? Secondly, can we get something that works for Q that's a lot closer to the 2 delta that was used in Jerom's sequential algorithm? Okay, so sequential, not sublinear time algorithm. So I think there's a lot of nice questions there, but I think in general, this question of uniform generation in local algorithms for uniform generation has very little work done in it. And I think it'd be interesting to see what other problems one can uniformly generate. Okay, so this is the part of the talk. How much more time do I have? Okay, so this is the part. Oh, hi, Elad. How much more time do I have?
Yes, you have at least 6 minutes, at least.
Okay, great. So so this is the part of the talk where I'm going to switch the model on you. So I do want to talk more about generating large random objects, where we don't want to have to generate them up front. We'd like to generate them locally on the fly, but I am going to switch the model now. from what we talked before. I had in the local algorithms model that you don't get to remember anything. It's bad to remember. You want to talk to your friend. You don't want to have to talk to your friends. You want to be able to just do things. Now I'm going to switch to a model that's weaker. The only thing, and this, I have to switch to this because it's the only way we know how to solve these problems. However, I think some of these, if one, an open question is maybe for some of these problems, you can do better and give something that works in the LCA model. We saw that for coloring, you can do something in the LCA model. Now, some of these other problems, maybe you can do something in the LCA model for these as well. But so far, we don't know how to do it. So I'm going to define a weaker model. Here, we have what we call a local generation algorithm. There's a user that queries. But now we can save memory about our past decisions, and we can remember previous queries, and we can remember how we responded to the previous queries, and we can figure out that we'll stick to and send them in the response, large random object, and the queries will increase our memory usage. So as we ask more questions, the memory we use is going to get, okay? So this is not appropriate. For example, if you have a bunch of agents answering independently, but we're still going to want sublinear probe complexity. Okay, so we want to answer in sublinear time. We can store past decisions, but we still want the output distribution to be epsilon close in, say, L1 distance or whatever distance you like to the goal distribution. Okay, so here's an example of something simple you can do. What if you have a very long one-dimensional random walk on the line? Okay, with probability half you go up, with probability half you go down. And the kind of query you'd like to ask is at time t, how high were you in this random walk? Okay, what is the number of times you went up minus the number of times you went down? Okay, and perhaps you query about time t prime, time t double prime, and you get responses at each of these, and these queries can appear in arbitrary order. But what you'd like is eventually, if the user asked about all of these times, you would get something that is a legal path and generated from the uniform distribution. Okay, so when you ask all the queries eventually, there shouldn't be gaps. It should all be a legal path, and it should look like it came from the uniform distribution. And it turns out for this problem, you can use techniques of Gilbert et al. And Goldreich et al., which allow you to do local generation of the hypergeometric distribution to solve this problem in a local manner. But you will have to remember things. Okay, so this one you can do. But what about more general random walks? This is random walks on the line. Let me mention also random Catalan objects. These are parentheses. You can have parentheses and brackets, parentheses, brackets, and braces. So random dike paths. These are also connected to random rooted trees and random walks where you're not allowed to go below 0. And in this work, you not only want to know what is your height at time t, which would tell you what is your nesting depth, you may also want to find your matching bracket. Okay, so we call those first return queries. And how would you be able to figure that out as well? Okay, so I will just say that we can do this in polylogarithmic time. I'm not going to say anything about it because I think I only have 2 minutes left. More generally, you could ask about random walks on graphs. Given a huge graph G and a starting vertex S, what is the location of the random walk at time t, where t is a very long time, okay? Now, for special structured graphs, such as the hypercube, cycles, Cayley graphs, and any graph that can be formed as a tensor or a Cartesian product of a small graph, we can get polylogarithmic time generators. We can answer in polylogarithmic time. For arbitrary graphs, it's more, it's unknown, But for graphs with spectral expansion lambda, we can get 1 over 1 minus lambda times root n as an upper bound. And that's fairly tight. As for random graphs, we know we need omega of square root n. And this is a case where the lower bound is actually quite a bit more complicated than the upper bound. And I think I don't have time to show you the upper bound. Maybe I will take a minute and show you the upper bound. But this is relatively straightforward. So given a query to where are you at time j, let time I and time k be the previous, let's say, nobody's queried and you haven't figured out any of the locations in this area, but you do know where you were at time xi, and you do know where you will be at time xk, okay? And all these places you haven't figured out yet. And you want to figure out where are you at time j, okay? So if j is far from both I and k, and what do I mean by far? I mean like omega 1 over 1 minus lambda times log n, then, we're going to, no matter where I was at time xi, if I take a random walk of time j minus I, I'm going to be at stationary distribution again. So I can just output here according to the stationary. Okay, so that's an easy case because I'll just output here according to the stationary and I won't figure out anything about what happens in between. Okay, maybe xj is close to xi and far from xk. Then I have enough time, no matter where I end up at xj, I have enough time to get to the stationary distribution at xk. So it doesn't really, so I have a lot of leeway here. What I'm going to do though is since I'm close to xi is I'm just going to take the walk. I'm going to start at location xi and take a walk of j minus I and write down all those locations. Okay, so just going to write down all those locations in my storage, and wherever I am is where I am. I wrote that down. Okay, the kind of harder situation is when I'm close to both I and k. Okay, so I need to find a path from xi to time j. J is my query time, so I need to find a path from xi to my query time and a path from my query time to xk. Okay, and I need them to be consistent with, I don't know where I am at time j, but I need to find a place to be where I'm consistent both with the walks that start at xi, which may not reach uniform distribution yet because I'm pretty close to xi. And I also need to be consistent with the walks that end at xk. Again, there's no time to be at like a uniform path. So what we're going to do is just pick a bunch of, okay, so the first try would be take random walks from xi until you find one that hits xk at time k minus I. And then wherever I was at time j, output xj. Okay, and the problem with that is that takes omega n time because in general, that could take omega n time. So what we're going to do that's a little bit smarter is take a bunch of walks starting from xi and a bunch of walks that end at xk until I find a midpoint collision. I expect to see that in root n time. And at that point, I can output, I'm going to stitch together these colliding walks. So these walks, whatever okay, that's not what I meant to do. I had some walk that reached here and some other walk from here that reached here. I'm going to stitch them together, and wherever I was at time j, I'm going to output. Okay, and that takes something like root n time because that's what I need to find a collision. All right, so I'm going to skip this because I've already gone over. I think there's a lot of open questions here, other huge random objects, and if there's some way to avoid the need for long-term memory of past decisions. There's lots of open questions in these areas. I mentioned the role of sparsification. I mentioned the issue of how to handle larger degrees. Lots of problems haven't been addressed at all. Improving the results we have for the problems that we have addressed are open questions. So I hope that I've convinced you that there's lots and lots of open questions here, and lots of great colleagues are working in this area that have, the colleagues that I've been working with have wonderful ideas and are very creative. So it's wonderful to work in this area. And I invite you to join us. So that's it. Thank you.
Thank you very much. Are there any questions from the audience? if you do have a question, please just go ahead.
Okay. I just want to thank you. It was wonderful. And, I was kind of stick to my chair and, I listened to every word.
Thank you. I'm
So,
glad that
yeah,
you did.
thank you. Thank you.
Thank you.
Okay. I also enjoyed the talk very much, and I even saw the connection to self-stabilization with the memory limited model. I was wondering if you can say another word or two on the application of these wonderful algorithms.
I think so I think applications of these algorithms are it's a relatively new model. So I think as far as applications, it's relatively new, but already they have been used in a learning setting. And I think that other than the fact that I use them to do seating charts, say at the last minute for people in exams, I think it's sort of a place where the people actually already do it. For example, local algorithms for graph partitioning is already used, I think, in Google. Local algorithms for matching is something that people may use in specific settings. Maybe this, but I think figuring out what other people would have done is something pretty natural. So I expect that it will have more applications than it does right now. And I also expect that we'll find places where people actually use it without telling us. And so in a lot of heuristics and in a lot of places where they need to figure out what to do, but they just don't have time. So I would imagine that we're going to find more and more places where these things are done. I'm sort of curious to see if in these natural algorithms with the ant colonies, and if people don't find that what these groups actually do are local algorithms. Like the ants they are sequential algorithms. Each ant is by itself a sequential algorithm, and he has to figure out how to optimize. So I'm curious to see if they one day find out that they're using local computation algorithms. But I think part of it is just to be seen, and that maybe is maybe that's an open question that I didn't mention yet, but maybe is one of the more interesting questions in this area is where are these things already used, and where can they be used to help in sequential computation?
Yeah. This is very nice. Thank you very much for the talk, and by this I close the last session of the day, and we will see you all tomorrow.